All right, so we're in the middle of this unit on bonding. And today we're going to start talking about the third and final type of bonding that we're going to discuss this year, and that is covalent bonding. But before we do that, I've prepared a little bit of a presentation to remind us of where we've come from. Back a bit over a month ago, we started talking about electrons. We're going to start there and come up through what we've talked about so that we can understand covalent bonding in the context of what we've learned so far. Now, to add further excitement for both you and I have made this presentation and these slides all having to relate to food. So here we go. Why do things bond? Why do things bond? This is the first question we have to ask ourselves. Why don't we have a universe filled with pure elements? Why do things prefer sometimes, many times, if not most times, to combine together into compounds? Well, that has to do with their electron structure. We learned all about how electrons are placed around the atom, right? Good illustration of that are these red onions here. Look at the nice rings there. Very representative of the shells, the energy levels of an atom. And we learned that each of those energy levels represents a different size orbital in which the electrons are located. And within those different energy levels, we even have different shaped orbitals and different numbers of orbitals. But what we focused on recently are these outer rings here, these outer energy levels. And you might see from the onions coming together why that is, especially when we're talking about bonding. Because it's the outer layers that come together when things interact, when things bond. And we learned that a great deal of stability comes when an atom has what's called a full outer set of electrons, which we call valence electrons. And we also learned that looking at the electron configurations, that the maximum amount of valence electrons that any atom can have is 8. And that seems to be, as we look at the noble gases, which all have 8 valence electrons, to be a very stable electron configuration. And in fact, through further observation, we've seen that other elements get that same electron configuration through bonding. And that we know is called the octet rule. The octet rule states that when they bond, elements want to achieve a noble gas electron configuration, which, as I said, is 8 valence electrons, or in the case of hydrogen, would be 2, right? Because it wants to become like helium. So the first way that can be done is ionic bonding. Ionic bonding takes place between metals and nonmetals. Now, if you look at the metals and where they're located on the periodic table, you can see that they can become most easily like the noble gases by losing 1 or 2 or 3 electrons, whereas the nonmetals have an easier time gaining electrons, 1, 2, 3. And that's what atoms will do. They'll either lose or gain electrons to become stable, whichever is easiest for them. In an ionic bonding situation, a metal will get together with a nonmetal. The metal wants to give, the nonmetal wants to receive, and as you can see here in the picture, one gives its electrons, or in our case pasta, to the other. Both are happy and they become attracted to each other as a result. The one that's received electrons, extra negative electrons, it becomes negatively charged. The one that loses its negative electrons becomes positively charged. Voila, they become attracted to each other and can form these ionic bonds. So how do metals bond together? What if you don't have someone that wants to give and someone that wants to receive? What if you have only metals who all want to give away electrons? How do they become stable? Where do they give the electrons to? They have no nonmetals around to give them to. Well, the answer is they give them to the spaces in between the metal atoms. When they do that, you might imagine that all of the atoms, because they're metals, become positively charged if they all give them away. Well, wouldn't that lead to them being repulsed by each other? Positive repelling positive. Well, I tried to find a slide where two people were angry over each other and fighting over the same piece of food, but wouldn't you know, there are no pictures of humans doing that. So I had to resort to these two seagulls who look really angry at each other. They look like they don't like each other at all. But they both do like that fish. And because, as in the case of metal atoms, because they've given electrons and those electrons are hanging out in the spaces in between them, because they're both attracted to the electrons in between, ultimately they're held to each other. Just like these two seagulls are glued to each other because they're both hanging on to the same fish. We call this, by the way, the sea of electron model, because the electrons in between those metal particles are able to move around and flow like water through the atoms. Finally, we're up to date. We're where we're at. The third and final scenario would be, what if you get nonmetals and nonmetals together? What if you get two atoms that, in order to become stable, need more electrons? In this case, where do they get them from? They've got no metals from which to get them. So in this case, they share the electrons by both using some of their valence electrons. It's like those electrons count for both of them, and they both can be satisfied, both can be stable. Great example of this, you're watching a movie and you pop a bowl of popcorn. And so the two of you or three of you are sharing this popcorn, watching the movie, and you might have been in this situation. Take these three little girls. They're evenly sized. They look like they're kind and would share well with each other. And so that popcorn bowl is going to be passed around evenly. They're each going to get their fair share of the popcorn, and everybody's going to be happy. But that doesn't always happen. Sometimes you get, as in the case of my marriage, a popcorn bowl that doesn't always get shared evenly. In fact, it's funny, not 2 weeks into my marriage, my wife announced that she no longer wanted to share with me. Can you imagine that? But she had good reason, because when we shared a sundae or a bowl of popcorn, inevitably, she felt like she didn't get her fair share. I'm like the woman on the right who always seemed to have the bowl of popcorn on her lap instead of the person that they're sharing with. And my wife always felt like she had to eat hand over fist quickly to even get her fair share. So now we both get a bowl of popcorn if we're eating popcorn together. But look at this scenario. They look happy. They look like they're having a good time. But maybe under the surface, as you can see from the positioning of that woman on the left there, that she's having a hard time getting her fair share. The electrons, or in our case the popcorn, is spending more time on the woman on the right's lap than on the left. And so if these were two atoms bonding together, then those electrons, because they're spending more time around the woman on the right, or the atom on the right in this case, they're negatively charged, and that would cause a charge buildup on the right-hand side. Whereas in the previous example, when the electrons are evenly shared, spending an even amount of time around each atom, there's no charge buildup. And so these are called polar bonds, as opposed to the prior example, which are called nonpolar bonds. And so this is just an introduction to covalent bonds, in light of what we've talked about before and the other ways that things bond together, and some of the different concepts that we're going to discuss. Covalent bonds being bonds resulting from the sharing of electrons, and how even though electrons are being shared, sometimes they're shared evenly and sometimes they're shared unevenly. And that, as we'll find out, has a great deal to do with how the compounds form and their properties.